So please go ahead, Patrick.
Okay. So I will talk about the topology. So the topology of the electronic structure of the topological insulator then samarium hexaboride as determined by density functional theory plus DMFT. It will be about equilibrium calculations, but of course, since we get a good understanding of the topological mechanism, then this can also be useful if one then considers what happens if you introduce a time dependence in the system. So first, I have a short motivation, both experimental motivation and also from a theoretical point of view, why it's interesting to look at this. Then I will briefly go into the calculations and show the results and compare with experiments. The main part of the talk will then focus on the topology and how to understand it in detail, and then a brief summary and conclusion. So from an experimental point of view, there is actually a huge body of work related to samarium hexaboride and whether or not it's topologically non-trivial. So everything started actually from a theoretical model by Di, where they analyze a simplified model applying Kondo renormalization and then saying that, oh, if we do this, then it looks like samarium hexaboride would fit this model and therefore it should be topologically non-trivial. And then samarium hexaboride being one of the well-known Kondo insulator, so-called Kondo insulator, had some mysterious properties before that one couldn't explain. So then a lot of experimentalists jumped on this to see if this could be true, because if it's a topologically non-trivial, then it needs to have metallic surface states. That's one of the predictions. And that could also explain some of these more mysterious properties. So one of the earlier experiments was where they measured then the conduction or the resistance using different samples, a thicker sample and a thinner sample, and then they compare then the resistance ratio to see because if it's insulating in the bulk but has surface metallic surface states, then the thickness shouldn't matter. And then at higher temperatures, then you have some conduction in the bulk, and then the thicker sample has a lower resistance. But then as you go to lower and lower temperature, then both samples, thick and thin, goes to the same resistance ratio, meaning that in this case, the conduction is only at the surface, which would then say that you have these metallic surface states. If you then dope it with a magnetic impurity, then this would, from a theoretical point of view, disrupt the topology if you include magnetism, because it breaks time reversal symmetry. And then for these samples, they say, look, here we still have, here it's actually not only surface states giving the conduction. However, then other experimentalists started to do photoemission experiments to really look at the surface states. And indeed, they find surface states, but then the question, but what they saw was that, okay, you had these, so this is the Fermi surface, then they saw, aha, we have these pockets around the X point. So this is gamma and this is X. But if it's supposed to be topological, then you cannot have an even number of pockets. And the theory predicted that you would have something here in the middle around the gamma point also. Then also other experiments came, and then they saw that, oh, we do have some weight here at the gamma state, but it doesn't connect to the bands lying below the Fermi energy. So it's like a parabola instead, and this can easily be lifted above the Fermi energy due to some change in the surface potential. So therefore, they say that this is, they say that this is Radboud states that were split, and they are trivial. And then they say, aha, no, and this pocket, they say, this is an umklapp state, where because they have, in this experiment, they saw actually another big ring here, but they say it's an umklapp state from these X pockets. But other experiments said that no, it has to be topologically non-trivial, and there is a big discussion around it. From the theoretical motivation, then one can see that in order to determine the topology of a system, in this case, that you have you need to have time reversal symmetry still there, and if this is sort of your only symmetry, then one talks about this Z2 invariant. But all of these topological invariants are fundamentally connected to having an efficient, effective Hamiltonian. They are, in essence, directly connected to one particle effective Hamiltonians, because they, if you go into the details, the topology is directly connected to the phases that are picked up by the eigenvectors of this effective Hamiltonian as you gradually change your K adiabatically through the Brillouin zone and connect back through a loop to the same starting point. And if you have inversion symmetry in time reversal symmetry, as in samarium hexaboride, then it turns out that instead of integrating up these phases, it's equivalent to count the occupied bands and check their parity. And you want to have an odd number in total if you check all the trim points. So the gamma, X, M, the points where the K points map back to themselves if you apply time reversal symmetry. So at this point, you want to count the bands and see if you have an odd number for a certain parity. Then you say that it's topologically non-trivial. But if you have an even number of bands in total, pair of bands, then you say that this is trivial. So you can, but as you see, it's directly connected to having an effective Hamiltonian of the system. However, with samarium hexaboride, it has a multiplet structure, and you have a lot of poles in the self-energy, and these poles can, well, gradually smear out the bands and make them disappear, as you see here. They smear out, they don't have unit weight, and so the question is how to even count the bands if they have just fractional weights. Do they count as 1 or 2? So in order to look into this, I wanted to see if I could do something more rigorous. Then there was also the question that most studies have been using this so-called topological Hamiltonian, which I will talk about more later on. But in principle, it's where you take the Hamiltonian, your DFT Hamiltonian, and then you simply add the self-energy at 0 frequency. So you take your Matsubara self-energy and then you extrapolate it to 0 frequency, and then you add it to Hamiltonian, and then you say, this is my effective Hamiltonian. This is the one that I should apply this Z2 invariant to. However, some studies for model systems said that, yeah, it seems to work, but in some cases, in some rather rare cases, it seems to break down. And that's also was a bit confusing, because the paper where it introduces it, from there it looks like it would be generally valid to only look at the 0. So the question was, did they miss something in their derivation? Then there is another way of constructing an effective Hamiltonian, which is then this pole extended Hamiltonian. And so this one, since as I will show, it captures all the poles of the self-energy, this would be a better, more rigorous starting point. So that was what I wanted to look at. So now comes the results. I had already been doing DFT plus the Hubbard 1 approximation for samarium hexaboride in an earlier work. So I knew that DMFT seemed to give really accurate results. However, with Hubbard 1, you get pretty accurate results on the EV scale. But in this case, I really wanted to look at what happens close to the Fermi energy. And unfortunately, Hubbard 1 did not cut it there. It was too inaccurate, so that it didn't give, it gave a band gap, but the Fermi energy did not go into the band gap. So it's sort of metallic. So therefore, I ended up I wanted to add some bath states and see if this could help to get a more accurate description close to the Fermi energy. So to describe the material, we have the samarium 4f orbitals, and they are strongly correlated. They have a U about 80 V, which you actually can see because it's a mixed valence system, meaning that you have some states that are normally have 6 electrons, and then you have many body states that have 5 electrons, and they are so close in energy, in this case only 12 millieV apart, that at the temperature we looked at 100 Kelvin, you have a thermal occupation, meaning that you can see transitions from 6 to 5 in the spectrum. This is here. The red is experiment and the black is the calculation. Then you also see the transitions from 5, having nominally 5 F electrons, to 4. Here in this experiment, this is taken this is a on resonance experiment, which means that it in this case emphasizes the 5 to 4 transition, which is why the weights are quite off. But if I do this calculation now, adding a few bath states and also correcting for very high energy bath states, then I'll get valence, the number of F states to be 5.48, which is in close agreement with the experiment. This number, though, it depends on the double counting, of course. So the way I set the double counting was, in order to have an as accurate description close to the Fermi level as possible, I wanted to make sure that I had the same number of electrons within the impurity problem as in for the lattice Green's function. If you do quantum Monte Carlo, then the local Green's function is the same as the projected lattice Green's function, also within the solver. But in ED, since you discretize the bath, then the impurity problem, there you may not have the same number of electrons unless, well, so in this case, the double counting was set to give exactly the same number of electrons, to give an accurate description at the Fermi energy. And in this case, so in this sense, the double counting was not a parameter I set, but it was varying itself, and at self-consistency, the number of electrons went to this value. In addition, which is good, that is that the lowest lying multiplets, so gamma 1 and gamma 8, were actually exactly the same as what's picked up in the experiment, where other studies had instead gotten the gamma 7 as the first excited state. So then from the theory, I could then get my band plot. And here is the bulk bands, now zoomed in quite a lot close to the Fermi energy. And indeed, we get a band gap, and the band gap is around 9 milliV-ish. It depends on where you count to the edge, or if you count to the peak to peak distance, then it's larger. And that matches well with the experimental value of around 10 to 15 milliV. So here is the theory, and then here is one experiment where they looked at the photo emission intensity from gamma to X. So this part can be compared to this part, and you see here we have the spectral weight, and that matches experiments. Then we have the bands over here at around 15 to 20 150 to 200 milliV, which matches well here. We have the dispersive band coming here and here, which is reproduced here in experiments. But then, as you see here, that's the signature of a surface state, which I don't have in the bulk calculation. So therefore, in order to see if I also get the surface states, I did supercell calculations with and I used two different surface terminations, because in the experiments, they know that the surface rearranges when they cleave the sample. It's a bit unclear exactly how it rearranges, but it's they can be quite sure that you have some surfaces that have predominantly a boron on the surface, which I calculated here, and other surfaces where they have predominantly a samarium atom sitting at the surface, which is the case here. So in these calculations, then I get these surface states. So instead of having a gapped system, now you have these surface states. in addition, you have, coming from these outer boron layer, you have two parabolic bands coming down, and depending on how you, depending on the surface potential here, that is sensitive then to the reconstruction, these bands may come just below and touch the Fermi energy. So from this, given these results, yes, we would see here, so this was with a B6 termination, then we had a strong bands coming down, the surface bands, but we also had these bands around the X pockets, and we do pick up this band here. That is what is required also from a topological point of view, because then these were 2 and this 4, 5, 6, 8, 9. So we have an odd number of bands. So at least it's not a contradiction that it has a trivial topology. So it seems like it should have a non-trivial topology. So this, and here we have the experiments again in comparison, and these experiments had predominantly a B6 termination, although they waited some time before they took their spectra. So they don't have these strong parabolic states that dip down. Because if you wait a bit, the surface reconstructs, and then these two parabolic bands start to be lifted above the Fermi energy. So given this, our interpretation of the experiments would be that, yes, indeed, this weight here around the Fermi energy, it is trivial bands in the sense that they are parabolic and they can be lifted above the Fermi energy. But we would say that their interpretation, that this band here, or in their experiment here, would be an umklapp state is not the actual, is not correct, but instead this would be the missing topological surface state. But however, now this is only comparing the bands. It's of course best to have an actual topological, evaluating the topological invariant. So to outline this part, I will go into this pole expansion Hamiltonian that I used, which is then a rigorous starting point, because it becomes an effective Hamiltonian that fully captures the Green's function. And this effective Hamiltonian is based on the pole expansion of the self-energy, and that the self-energy is made out of poles can be shown by using the Lehmann representation for the Green's function and combine it with the Dyson equation. To go into a bit more detail, so the self-energy has both a constant term, the Hartree-Fock term, but it also then has a dynamical part which looks like a hybridization function, in the sense that you have some weights, and then you have some energies. So this part looks like a hybridization function that has this form. So one can then interpret the poles of the self-energy as if they were just additional auxiliary orbitals that we would add to our system, which is exactly what Savrasov did in his PRL in 2006. And then if you do this, you can write your Green's function on this matrix form, where you add the Hartree-Fock part to the Hamiltonian, and then you have here your self-energy, but written out in matrix form, and this is your Green's function. Doing this, we can now use a well-known matrix identity that any inverse on this form can instead be is identical to doing this calculation instead, that you attach these so-called auxiliary orbitals to and create a big auxiliary pole expanded Hamiltonian. Then you create then the Green's function, which is now effectively non-interacting Green's function, because this is just a big non-interacting Hamiltonian, except that you have these additional auxiliary orbitals corresponding to the poles of the self-energy. And then you take the inverse, and this Green's function you project again upon the physical orbitals. So you project out the auxiliary orbitals. Then, so from this, one can say that all bands in the physical, for the physical Green's functions will then correspond to eigenstates of this effective Hamiltonian, the pole expanded Hamiltonian. However, when you do the projection upon the physical orbitals, that's when the bands gets a reduced weight. Just like if you have a density of states and you make the projected density of states, you also lose weight. In this sense, you lose weight from the auxiliary part, from the auxiliary orbitals. This also means that if you have topological surface states, this means in your for your lattice Green's function, then they will correspond to having topological surface states from your pole expanded Hamiltonian. You cannot have states, you cannot have surface states in G unless they also show up in the full, for the full topological Hamiltonian. This, and what's good is that this Z2 invariant is of course very well defined on this pole expanded Hamiltonian. Because it's an effective Hamiltonian, it's non-interacting, so you can simply apply it. However, the problem is, of course, that it's very, very difficult to get the explicit poles of the self-energy. You can, in principle, do it from an ED with the ED solver, but with a general solver is more or less impossible. But in the case of DMFT, we can be a bit clever because we can use the symmetries of the system, and we can use that the self-energy in DMFT is local. That means that only this Hamiltonian has a K dependence, while the self-energies lack a K dependence. So in order to use the Z2 invariant, of course, the first criteria is that it has to be an insulating system. Otherwise, it cannot be a topological insulator. However, we then must know that there are no poles of the self-energy well, since we don't know the poles of the self-energy directly, or rather, we don't know the eigenvalues of the full Hamiltonian because we don't construct it, then we must make sure that the full pole extended Hamiltonian still is gapped. And the way to do this, since we know that the self-energy is K independent is that we first look at the self-energy and see, does it have a pole at the Fermi energy? And in this case, for some arm hexaboride, the self-energy does not have a pole at the Fermi energy. So we know that there are no energies, there are no poles here that cross through zero. So then comes the question, now that it connects to the Hamiltonian here, that is K dependent, will there still be no pole that cross the Fermi energy? And what we also know is, if we look at the Green's function that we construct using our self-energy, we see that remains gapped in the bulk. However, if this means that also the full Hamiltonian is gapped, because the only other option would be that a completely auxiliary band crossed the Fermi energy, but we know that it cannot be completely, if it was completely auxiliary, then it could not have a dispersion, because the self-energy is dispersionless. Hence, the full Hamiltonian, the full PE Hamiltonian, although we cannot construct it explicitly, we can know that, it will be gapped. So then the second thing we must make sure now is, how to evaluate this Z2 invariant. And we know that in this case we only apply the self-energy to the F orbitals, and that was enough. We saw that it was enough with the local self-energy on the F orbitals to reproduce the experiments. However, since the self-energy is local, we also know that if we represent it with auxiliary orbitals, these orbitals must have the same irreducible representation as the F orbitals themselves, because otherwise they would not hybridize. This means that they will also have the same parity as the F orbitals. So if we look at exactly the trim points, then since they have odd parity, they will not connect to the even parity orbitals at these trim points. So in essence, the self-energy will only connect to the odd parity sector and not to the even parity sector.
Hi, Patrick, you have 10 minutes, including questions.
Okay, then I will very soon be done. So it's enough to count the bands in the non-interacting channel. And this one, since it does not connect to the self-energy, it's basically looks very close to the DFT starting point, except for a small shift due to the self-consistency of the DMFT cycle, of the charge self-consistent DMFT. And if we count the bands, we see that, it is odd. And if it's odd in one sector, it must be odd in the other. So then you see that it is a non-trivial topology from this. So then finally comes the question, so now we use this rigorous pole expanded Hamiltonian, which directly connects to the spectrum. But what about this topological Hamiltonian? Is it still okay, or why did it break for some systems and not for others? So indeed, one can actually perform a continuous interpolation between the pole extended Hamiltonian and this topological Hamiltonian, but you have to add the auxiliary orbitals like this. And you can do this interpolation if you vary the lambda from 0 to 1. You go in between these two, and you can show that you're not closing the band gap. If both of them had a band gap, then this interpolation does not close the band gap, and this means that they are in fact topologically equivalent. So this means that this topological Hamiltonian works as long as the contribution to the topology from these auxiliary orbitals is trivial, because you get a contribution from the topological Hamiltonian and you get another contribution from the auxiliary orbitals that you, in the framework of only looking at the topological Hamiltonian, you neglect this part. However, for DMFT, we know that these auxiliary orbitals, they correspond to the poles of the self-energy, and for DMFT, then the poles are k-independent, so the auxiliary part is automatically trivial. Which means that with a local self-energy, it is okay to use the topological Hamiltonian, that it works. However, if the pole structure of the self-energy has a k-dependence, and if this k-dependence is topologically non-trivial in the sense that this auxiliary Hamiltonian has a non-trivial topology, then the topological Hamiltonian approach breaks down. So you get a non-trivial contribution from the non-local self-energy, which is interesting, because then if one treated this instead of having using DMFT, so DMFT works for some-arm hexaboride, but for other systems it may not work. So if you then use, for example, dual fermions or D gamma A for a system, and then you get a non-trivial pole structure, then you would get another topology of the system. So to summarize, DMFT does a good job for some-arm hexaboride. We get an intermediate valence at 100 Kelvin. There is a gap, and we get topologically spin-protected, spin-polarized surface states. We really saw that they were indeed topological surface states, since we could evaluate the topology of the pole-extended Hamiltonian. In addition, that we saw also that the topological Hamiltonian, where we only add the self-energy at 0 Matsubara or 0 frequency, this breaks if we have a topologically non-trivial pole structure in the self-energy. And more details and explicit examples are given in this archive version. Thank you very much.